In this paper, we experimentally analyze a few of BSDF models in terms of their accuracy to represent measured BSDFs, their required storage sizes, and computation times. Photorealistic rendering can be seen as a variant of computer graphics that addresses light interaction and accurate descriptions of materials involved in a scene. Optical thin translucent materials such as papers, glasses, and daylight redirecting films are represented by bidirectional scattering distribution functions. The BSDF is a sum of bidirectional reflectance distribution functions and bidirectional transmittance distribution functions. Therefore, it represents both light reflection and light transmission of translucent materials. In photorealistic rendering process, measured BSDF data can be represented by an analytical BSDF model or a data-driven BSDF model. Since measuring four-dimensional BSDF data is a very time-consuming process, there is only the building material example BSDF database in the literature. The BMA database was constructed by FEM benefits and includes BRDF, BTDF, and BSDF measurements. BMA database includes measurements from frequently used materials, and it does not include measurements from highly anisotropic or complex translucent materials. We feel that there is a need for a large BSDF database which consists of measurements from isotropic, anisotropic, and complex translucent materials. We also feel that an experimental analysis and comparison of BSDF models are needed. In this work, we measure optical thin translucent materials by using PG2 gonophotometer. PG2 gonophotometer consists of a sample holder, a light source, and a detector. A variety of sample holders can be used depending on the material. Light sources are mounted on a standard optical bench, including collimating optics and custom baffles. The detector is mounted at the end of linkage, consists of two lightweight arms, and it is moved fast at a constant distance around the sample center. PG2 gonophotometer measures BSDF data in spherical coordinate system. Measured BSDF data is regularly sampled at both incoming and outgoing directions. While PG2 gonophotometer allows many outgoing angle measurements, it allows only a few number of incoming angle measurements. Therefore, we get BSDF measurements that are irregular and sparse. While these BSDF measurements can be represented by an analytical BSDF model, they must be preprocessed before representing and rendering by a data-driven BSDF representation. By using PG2 gonophotometer, we measured BSDF data from three samples of optical thin translucent materials, namely Hunter-Douglas, orange glass, and structured glass. Structure of Hunter-Douglas is mostly reflective and diffuse. Orange glass materials is isotropic and glossy. Structured glass is anisotropic and glossy. We constructed a BSDF database which includes measurements from all of these measured translucent materials. Our BSDF database can be used for validation, simulation, and comparison purposes. The acquisition time amounted to approximately 2 days for each BSDF measurement. We choose one analytical BSDF model and one data-driven BSDF model for our analysis. Walter et al.'s analytical BSDF model and Ward et al.'s data-driven BSDF representation. These BSDF models differ in their degrees of freedom and goals, and we focus on the numerical ability to fit our measured BSDF data, computation times, and storage needs. Walter et al.'s analytical model is based on the microfacet theory, and it is for representing raw glass material. In their work, Walter et al. Introduced GGX microfacet normal distribution, which works extremely well when it is compared to Beckman distribution for representing raw translucent materials. Walter et al. Also proposed important sampling techniques for their BSDF model, which is essential to Monte Carlo rendering algorithms. The reflection part of the Walter et al. BSDF model is similar to Cook-Doran's BRDF model, and we restrict reflection part to have only one specular role and the diffuse contribution to be Lambertian. To compute Fresnel term, we use the Schlick approximation. To compute G term, we use Smith approximation. To compute G1 and D term, we use the following GGX distribution. One of the core parts of our analysis is to fit measured BSDF data to Walter et al.'s analytical model. In this work, we extend Negan et al.'s fitting procedure to represent measured BSDFs by Walter et al.'s analytical BSDF model. We apply a constraint non-linear optimization technique and we estimate width parameters, index of refraction and Fresnel coefficients non-linearly by using a constraint minimization algorithm. Diffuse specular reflection and specular transmission coefficients are computed analytically as a sub-procedure based on a linear least square optimization. To optimize fitting results for finding a global minimum, we restart the optimization with a different set of initial guesses and we take a set of parameters which leads to minimum L-square error. Ward et al.'s data-driven BSDF framework includes two data-driven BSDF representation, matrix-based BSDF representation and tensor tree BSDF representation. This framework is readily available in Radiance Render and as an XML representation and an open source C library. The library allows for efficient representation, query, and Monte Carlo sampling of real-world BSDF in a model-free framework. In this work, we select to use the tensor tree BSDF representation because it helps to represent highly peaked data more accurately by subdividing BSDF data adaptively in different regions of the tensor tree BSDF representation helps to keep closely associated BSDF values near each other for a convenient subdivision. Tensors can be considered as a direct extension of vectors and matrices. We use rank 3 tensors and rank 4 tensors to represent isotropic and anisotropic S data respectively. In tensor tree BSDF representation, to map dimensions in the tensor tree BSDF representation to dimension on an each hemisphere, Charlie and Q mapping is used. Since our BSDF measurements are sparse and irregular, we need to fill these BSDF measurements accurately to be able to represent them with tensor tree BSDF representation. In this work, we use Ward et al.'s Lagrangian-based interpolation technique for filling our sparse set of incident angle measurements. Ward et al.'s method for reconstructing a complete BSDF from sparse irregular measurements proceeds in 3 stages. For each incident direction, measured BSDF values are fitted by a sum of Gaussian laws. Then a spherical denominator triangulation of the incident directions are constructed. Finally, for each edge of the triangulation, a transport plan is computed for shifting Gaussian lobes in the first vertex, the Gaussian lobes in the second vertex. To make an interpolation inside the triangles of the spherically denominator triangulated mesh, a method similar to nested linear interpolation of the transport plan is used. As you see that Ward et al.'s interpolation technique gives better results than a non-linear interpolation. To investigate abilities of the BSDF models, we used our BSDF measurements and BSDF measurements from BMA database. The nonlinear parameters of Walter et al.'s BSDF model is estimated by using fmin_con function in MATLAB library. fmin_con provides a constraint nonlinear optimization which attempts to find a minimum of a function of several variables starting at an initial estimate. We optimize L-square errors in this fitting procedure and linear parameters are estimated as a sub-procedure based on a linear least square optimization. To represent BSDF measurements with Ward et al. Tensor tree BSDF representation, we first interpolated it by Ward et al. Interpolation technique. To simulate both Walter et al. BSDF model and Ward et al. Interpolation technique in Radiance, tensor tree BSDF representation are constructed by using BSDF to tensor tree function in Radiance. This figure shows visual comparison of both BSDF representations. The figure includes comparison based on our BSDF measurements. Since Walter et al.'s BSDF model only considers single scattering term and it does not handle multiple scattering terms inside the material volumes, there are some inaccuracies and colloid decays in the representations of materials. Ward et al.'s BSDF representation has ability to handle more complex materials visually plausibly, and it tries to represent both single scattering and multiple scattering inside the material volumes. This figure shows visual comparison of both BSDF representation as well. The figure includes comparisons based on isotropic BSDF measurements from BMA database. As you can see that Walter et al. BSDF model only considers single scattering term and it does not handle multiple scattering terms inside the material volumes. There are some inaccuracies and color decays in the representation of materials. Ward et al.'s BSDF representation has ability to handle more complex materials visually plausibly, and it tries to represent both single scattering and multiple scattering inside the material volumes. Furthermore, we compare storage requirements and computation times of the investigated BSDF representations. Table 1 reports storage requirements that are used to render images in previous checkerboard figures. Wall et al.'s data-driven BSDF representation provides 10 times compression, or Walter et al.'s analytical BSDF model guarantees the most compact representation. On a 4-core laptop, average computation times of Walter et al.'s BSDF model and Ward et al.'s BSDF interpolation technique are 12 minutes and 46 minutes respectively. In this paper, we measured BSDF data from 3 different optical thin translucent materials and made experimental analysis on these BSDF measurements and BSDF measurements from BMA database by representing them with various BSDF models. We have shown that compared to Walter et al.'s BSDF model, Ward et al.'s data-driven BSDF representation provides more accurate representation, while it requires 60 times storage needs and 4 times computation times. We are planning to make publicly available our BSDF measurements and fitting results for giving a start to construct a huge BSDF database. I hope you enjoyed this presentation and thank you for your attention.